Hi, this is Alex from devstories.eu. Python, Cheminformatics, and AI, Episode 11 of 22. What if the best way to describe a molecule to a machine learning model is not with a handcrafted structural formula, but by treating its smiles string exactly like a sentence in natural language? You might be spending valuable compute cycles generating complex chemical descriptors, only to be outperformed by a text model. That tension is at the core of LLMs versus classical fingerprints. When predicting how tightly a ligand binds to a protein, your model needs a mathematical description of the ligand. The traditional route relies on classical structural fingerprints computed by tools like RDKit. You run a molecule through a deterministic algorithm and receive a static vector. A Morgan fingerprint counts circular substructures around atoms. MACCS keys check the molecule against a predefined list of chemical patterns. The limitation of these classical fingerprints is their rigidity. They encode specific, unchangeable rules. You cannot fine-tune them. If a particular structural nuance matters for a highly specific binding pocket, but the fingerprint algorithm was not explicitly designed to capture it, that information is completely lost before the predictive model even sees the data. Instead of hard-coding chemical rules, we can use a pre-trained chemical large language model like BioT5, GPT-2, or BERT. These models are pre-trained on millions of smiles strings. They learn the grammar of chemistry in an unsupervised way. When you pass a ligand to an LLM, it does not output a fixed checklist of functional groups. It outputs a rich vector embedding. Every character or token in that smile string gets its own contextual vector. To understand the difference, look at how these representations feed into predictive models. First, consider an XGBoost model using classical MACCS keys. You generate the MACCS fingerprint, which results in a simple binary array. You pass that fixed vector to XGBoost, which tries to map those raw presence or absence features to binding affinity. In benchmark tests across congeneric series, this specific combination consistently yields the poorest performance. The handcrafted features are simply too blunt. Now, swap that architecture for a BioT5 embedding fed into a transformer head. First, you pass the raw smile string to the BioT5 model. This returns a sequence of per-token embeddings. Then, you pass that sequence into a transformer head. Here is the key insight. The transformer uses an attention mechanism. It looks across the entire sequence of token embeddings and learns dynamically which parts of the molecule matter most for binding to this specific target. It weights the features intelligently before outputting the predicted binding affinity. If you try to take those exact same BioT5 tokens, sum them together into one flat vector and feed that into XGBoost, the predictive performance drops significantly. Sum pooling averages out the token-level details. The transformer head succeeds precisely because it preserves and exploits the granular context of the text-like representation. This shift from static arrays to dynamic embeddings offers massive practical benefits. LLM embeddings are highly versatile and can be fine-tuned for specialized downstream tasks. They're also much more compact than massive classical bit vectors, which saves memory when storing large molecular libraries. Furthermore, generating text embeddings runs on a GPU, which is drastically faster than computing traditional RDKit fingerprints on a CPU. The era of manually telling algorithms which chemical substructures matter is ending. The models that perform best are the ones allowed to read the molecule and decide for themselves. If you want to help support the show, you can search for DevStories EU on Patreon. Thanks for hanging out. Hope you picked up something new.